We're going to continue talking about definite integrals, but we're going to call it the fundamental theorem of calculus. And we're going to skip the first part of it and really just focus on the second part of it. If you're interested more in it, have a look at the text or Google around or ask me. I'd be happy to chat about it. So, fundamental theorem of calculus. What is it and why is it important? With a name like the fundamental theorem of calculus, you'd think it's fundamental. It's pretty important. So the second part of it, it's a two-part thing, is about evaluation. It tells us how to evaluate definite integrals. And I'm going to have my same sort of rant about notation, making it sort of needlessly complicated. So in any textbook, you're going to see if capital F has derivative little f, there's your first line. If capital F has derivative little f, then the integral of little f from over the interval from a to b is capital F evaluated for b subtracted by capital F. Anyway, what are we talking about? Well, remember, what it's really saying here is that this guy on the inside is the derivative of its kind of parent outside. We've been doing that with indefinite integrals. We've been thinking, okay, the integrand is the derivative of what function? We find that parent function, the function that has the integrand as its derivative. And then to extend it to definite integrals, it turns out that we take that parent function and we evaluate it at the upper limit of integration and then subtract it by the lower limit of integration, and you have a formal, complete answer for the definite integral. One that doesn't involve geometry like we were talking about last time. So that's all good and grand, but let me first just a bit of notation here. Oftentimes what you'll see is the integral from a to b of f prime of x, using my way of thinking about things, the derivative is the integrand, has what as its, what function is going to be, has f prime of x as its derivative? Well, f of x does. And so we see that this would give us f of x. If this was a indefinite integral, if there were no limits in integration, we'd add c there. But shorthand for evaluate this function, first at b, and then subtract it by a, is this vertical bar there. And so you can think of it as top minus bottom. Evaluate the function at the top and then subtract it at the function evaluated at the bottom. And sometimes, in particular multivariable calc, you'll see a little extra clarification as to what variable is being evaluated. But since there's really only one variable here, we oftentimes omit that, and this is what you're going to see as more common notation. So the point of the fundamental theorem of calculus is it formally relates the idea that we've had of anti-differentiation and integration. So let me try and kind of write this out using textbook notation. Sorry, my left-handedness is causing this thing to jump. F of x, big F of x, using their notation, is equal to integral of little f of x dx. And so what the fundamental theorem tells us is this guy on the inside has antiderivative capital F of x. And then capital F of x is the so-called, I like to call it the parent, the thing that has the integrand as its derivative. The parent function has derivative little f of x. And so, again, a needlessly complicated notation. There's a reason for it, but I think it's more intuitive to just think, okay, capital F of x is equal to the integral of what? Well, capital F of x has as derivative capital F prime of x as its integrand. And we see that the integral, the thing on the inside, is the derivative, and this integral sort of undoes the derivative. It's formalizing the, what does it mean to undo the derivative? Well, that is anti-differentiation. Formalizing this idea that integration is the opposite operation, if you will, on functions of differentiation. So that's enough of kind of the theory of it, really. I want to just dive right in and do a bunch of examples here. So to start off with, Last time we learned about the definite integral, that you could use it to calculate the area under the curve. And we did some definite integrals that we could do with geometry without actually having to do the integration. The fundamental theorem of calculus gives us that, hey, you can do the general integration and find the sort of original function and then evaluate it at the endpoints, and you will get the area underneath. But, so what does one hump of sine look like? Well, sine looks like this. One hump of it. And that goes from 0 to pi. That's what I mean when I say one hump of sine. It's going to top out at a height of 1. And that's going to be our area there. So to set up this integral, the area integral for this would be from 0 to pi of sine of x dx. And we know that ignoring the fact that we have a definite integral with bounds here, if this was an indefinite integral and didn't have the limits of integration, we could say, okay, sine is the derivative of, well, negative sine is the derivative of cosine, so negative cosine of x has derivative positive sine. And here, the fundamental theorem of calculus tells us that we can just evaluate this thing at x equals 0 and x equals pi and subtract those in the reverse order. So what's that going to look like? That's going to be negative cosine of pi for our first term. I guess I should be writing the, here, let me add this in. So if this is the derivative, f prime of x is sine of x, then the function f of x is cosine of x. And so what is this? Well, this is f of b, your top bound, minus f of a. Okay, so we're going to take that, we're going to subtract negative cosine of 0. We know what these values are. That's negative 1 minus negative 1. So that's going to be positive 1 plus 1 gives us 2. So this area right here, what we just calculated is that this has area equal to 2, which is kind of fun. We're going to pause this and pick up the next video.